Today we'll discuss about an elementary idea about beta decay. Now, as for the syllabus of paper 9, semester 4, physics honors, we don't have to go in detail of beta decay, but then what the syllabus required, only that we are going to discuss. So beta decay, basically it's a certain radioactive substance emits beta particles spontaneously. Now this phenomena is called the beta decay, right? So it has been proved that beta particles are very fast moving electrons, and it was shown that if the variation of mass with velocity of beta particle is not taken into account, their charge E by m was the same as that of electron. Now we'll just start with the properties of beta rays. After the introductory part, the properties. Number one is that it is beta particle, basically beta particles are very fast moving electron. Okay, their velocity, it may vary from 0.36 c to 0.9 c, where c is the speed of the light. Okay, now due to the relativistic speed, their mass varies with velocity. So as per the relation, m is equal to m naught by under root 1 minus b square by c square, where m naught is the rest mass of the electron. So accordingly, the mass of the beta particle, it's 1 by under root 1 minus b square by c square times that of electron. Now, as charge is relativistically invariant, the specific charge E by m of beta particle is less than E by m of electron. So what we can say that E by m of beta particle is less than E by m of electrons. Okay, now beta particles, number 2 is that beta particles are deflected. It is also deflected by electric and magnetic field. Okay, now the deflection of beta particle, it simply indicates that they are negatively charged. Number 3 is that they affect photographic plate. Number 4 is like they have ionizing power, but much less than alpha rays. Okay, now beta rays produces ionization in gas, though through which they passes, right? Number 5 is they have a high penetrating power, unlike the alpha particle. They have a very high penetrating power, nearly 100 times more than alpha rays. Okay, and number 6 finally is they can produce fluorescence, FLUORESCE, and phosphorescence. Okay, in certain substance like calcium, tungstate, barium, platinum cyanide, etc. Now, what is the origin of beta rays? Basically, now it is assumed that if we talk about the origin of beta rays, it is assumed that beta rays originate from the radioactive nuclei. Now, it has been shown by wave mechanics that the beta particle does not pre-exist in the nucleus, but is formed just at the instant of emission. It is produced by the transformation of proton into neutron with the simultaneous production of a new particle called antineutrino. Now, the process is represented by, you can represent this process by this equation z, and we will write y at plus 1, here we will write a plus e minus this much. So this is electron or beta particle. and obviously this is anti-neutrino. Okay. Now, anti-neutrino has practically no mass and no charge and is produced to satisfy certain conservation law that we know. Now, basically there are there are three processes of beta decay. Okay. So what we know is, number one is electron emission, electron or negative beta particle decay. Okay. It is called negatron emission. Similarly, we have positron emission, which is quite different from it, and then we have electron capture. Basically, the first part is known to everyone, the other two is also exist. Thus, there are three beta processes, that is negatron emission. Okay, then we have positron emission, and finally we have electron capture. Now, as far as electron emission is concerned, considering the first part, in the process of electron emission, a neutron is converted into a proton. So we write the equation. A neutron is converted first into a proton, okay, with the emission of an electron and an anti-neutrino. Okay, so if we take our parent particles, say x, a, z, okay, so now we'll have y, z plus 1, a plus e, naught minus 1 plus anti-neutrino. So if this is the parent nucleus which emits beta particle, that is the electron, then the process may be represented by this equation. Clearly, in the process of electron emission, the charge number of product nucleus is one more than that of the original nucleus. So, number 2 is positron emission. Now, we'll talk about positron emission. Okay, in the process of positron emission, a proton is converted. Here, a proton is converted, okay, into a neutron, obviously, with the emission of a positron. So, this is your positron. And a massless and chargeless particle neutrino. So this is neutrino. This is your positron. This is your neutron. And this one is your proton. So again, if we consider a general part, say this is the principal nucleus or the parent nucleus. So we'll have y z minus 1. Okay, a plus e on 0. Plus 0. And finally, the last one is electron capture method. So here the third one is electron capture. Okay, here in this process, the electron capture process, often termed as K capture, it is also known as K capture. Okay, the nucleus absorbs one of the electron from its nearest electron shell. Nearest means usually it is from the K shell, that's why it has been termed as K. K is the nearest cell nearest to the nucleus, emitting neutron. So in this process also, as in positron decay, a proton is converted into a neutron. So the process may be expressed as E minus 1 naught plus 1 P1. It gives you just this much. Okay. In general, if nucleus is, say for example, X, okay, ZA plus E minus 1 0, it will give you Y Z minus 1 A plus this thing. So a neutron rather. Okay, so this is what the three basic beta decay process, and in brief we will now discuss beta ray spectra. Okay, this has to be discussed in brief. The beta ray emitted from a radioactive substance have a continuous energy distribution which extends from 0 to well-defined maximum. So the maximum energy is characteristic of the radioactive substance. The energy variation of beta ray can be studied by a suitable beta ray spectrometer. Now a beta ray spectrometer enables us to find the positive number of beta particles possessing different energies. Now we'll show a curve over here. Okay, Now the curve shows the variation of relative number with kinetic energy. Okay, so we'll write relative number of beta particle. Okay, the y-axis, and this is your energy. Okay, so the curve showing the variation of relative number with the kinetic energy. Now the curve shows that the relative number of beta particle increases with the increase of energy. Okay, so you can show it over here. You can show it like this. Okay, and then it will go a slight bit higher. This is the highest one, and then it comes down. Okay, with increase, you can see that it increases with increase of energy, become maximum at a particular energy, and then it goes on declining. So it goes on declining. So this is your continuous spectra, right? So as far as the study of the curve obtained for a number of radioactive substances reveals the following, three following basically major part. And number one is like the beta particle emitted from a radioactive substance have a continuous distribution of energy. Distribution of energy from 0 to definite upper limit, and the upper limit is called the endpoint energy. The upper limit is called the endpoint energy. Okay, and is the characteristic of the nature of the emitter. Number two is, in addition to the continuous spectrum called the primary spectrum, some of the radioactive substance emitting beta particles are found to exhibit a series of sharp lines superimposed on a faint continuous background. This line constitute the line spectra. Okay, also known as secondary spectra. And finally, the emission of beta particle may not be associated with the emission of gamma rays. Okay, so say for example Na24, it emits gamma rays. Okay, whereas N13, In114, it do not emits gamma rays. This emits gamma rays, Na24, but this do not emit gamma rays. So this is the basic elementary idea about the beta decays. We'll continue to some other topic in the next lecture. Thank you.